Okay, so welcome everybody, IT 250 operating system. So ang atong our mechanics for this class, we are supposed to have, if this were a physical class, we would have a 3-hour lecture tonight, and we would have a 6-hour lecture tomorrow, and we would do that twice. Then the other instructor will cover similar 2 sessions, right? The 3-hour and 6 hours, so 9 hours, and 2 9-hour sessions. However, the way I'm going to execute this class is it's going to be asynchronous because majority of the activity you can do by yourself because we have AWS Academy, you can do AWS Access on the Cloud, and for the virtual machine items, you can actually do it in your own computers, in your own homes. So there's no need for us to be waiting on each other and spending 3 glorious hours just waiting for somebody to install Linux, right? So better to just use virtual machines, then we're going to make it an asynchronous activity. Most of the activities will have due dates and they will be posted in Moodle. Just make sure that you perform the said activity on the date that's specified. If you look at Moodle, oops, auto is gone. If you look at Moodle, all your activities are already actually ready. Of course, you don't see it yet because I think I hid it. So you'll have lab number 1 is installation of Linux. Lab number 2 is installation of the Secure Shell daemon. So these are activities that I will be telling you to do. Now there will be videos on using certain things, right? Here will be the Zoom links. Please take note, the Zoom links for each class is different, right? So today we're using this, tomorrow we'll use this. There's an introduction video to AWS because as you can see, we are using AWS in this class. And there's also installing CentOS and VirtualBox, which is what we're going to do right now after the lecture portion. I will try to keep the lecture portion at about 1 hour so that we don't have to finish the 3 hours tonight. Tomorrow, we will also do about 1 hour and 30 minutes just for certain hands-on portions that we do not finish today. Then you're going to have an asynchronous activity, which is basically your lab 1 and your lab 2, right? And hopefully we should have enough coverage tomorrow on the shell items so that you can do lab 3 asynchronously, right? So the deadlines will roughly be a week apart, so you have a lot of time to do them. Then you can ask questions to me. You can consult. This is my email address here in case you have trouble doing certain things or you don't know how to proceed. All right. So let's just make sure that you watch out. So the activities will appear. So you notice they're actually already there, but it says hidden from students. So they will pop up with their appropriate due dates once we cover those items. Okay. So let us begin. So first off, this is an operating systems class. So we will cover the basics of operating systems, why they are important, what role they function, and we will take a deep dive into operating systems. In this particular class, we're going to be using Linux because number one, it's an open source operating system and it allows us to look at the mechanics on how an operating system works, right? Of course, just for a quick introduction, I think there's a world market for only 5 computers. So the famous inventor, Thomas J. Watson, right, said this in 1943. But of course, clearly there are more computers. Like I think in this room alone, there are more than 5 computers already, right? So we have gone and improved and moved on from this era, and we now have computers everywhere in the span of less than 100 years, right? So trends in technology, right? This may not be the latest slide, but if you notice, everything gets better, right? Transistor densities, 35% per year. That means you pack more transistors into a CPU or a semiconductor, and the die sizes, semiconductors become larger. And therefore, if you combine the two together, you have a 40 to 55% per year improvement, right? So that means in 2 years, you will double the capacity of your existing semiconductors. That means computers hypothetically can double their speed every 2 years, which is actually Moore's law. Actually, the founder of Intel, Gordon Moore, said that every 2 years, semiconductor capacity doubles. And that's actually reflected here. Now we're hitting the limits of physics right now, but instead of trying to pack semiconductors into one die or one chip, what they're doing is they're doing multiple chips. That's the reason why your computers, your cell phones today have multiple cores. Second point is memory is also growing faster at 25 to 40% per year. However, if you notice, the growth in memory capacity is way slower than the growth in CPU capacity. As a matter of fact, we do have a global chip shortage, and majority of the chip shortage is actually in the memory space. Flash capacity, which is our disks today are mostly flash or solid state disks. That means they don't have moving parts. As opposed to the next bullet point here, which is magnetic disks. Now, magnetic disks are quite large. You can buy 4 terabyte magnetic disks in retail today, while flash disks tend to be at the 1 terabyte or 500 gigabyte range. Flash is still quite expensive, but they are much, much faster than magnetic disk technology, but they're slower than RAM. Right? So flash is like a glue. But because flash has become, the capacity has increased throughout the years, you will see a lot of flash machines, particularly laptops that are space conscious and gadgets like cell phones and tablets that use flash memory instead of solid state disks because of their smaller and thinner and lighter form factors. Right? And of course, networking technology is also becoming faster. So in addition to the improvement in the computing capacity, memory, and storage of our IT systems, even networks are becoming much faster. So for example, we have moved from 64 kilobits per second dial-up modem speed to 10 gigabits per second in only 20 years. So technology moves really, really quickly. And I think the moral story of this slide is that whatever we discuss gets obsoleted quite quickly. And that's the reason why we must keep up to date. Right? This is also another, it's not the latest, but up to 2012, you will notice the move towards improving CPUs. So this is like proof that Gordon's law still holds. Again, it's flattening a bit at the top, right? But it's still quite high. And what they're doing right now is they're simply increasing the number of cores to beat physical limitations. So why do we have to study, or why do you have to study operating systems? So what you want is because you want an operating system that is efficient. Now, operating systems are important because they actually manage resources. You see all the resources a while ago, CPU, memory, disk, and network. That's actually managed by an operating system because you don't want your applications to have to worry about managing resources. Number one. Number two is you don't want them to quarrel over resources. You want to be able to allocate a fair amount of resources for applications based on the prioritization defined by the user, which is you. And in modern systems, you do have multi-user systems, and that's the reason why it is important as well. Right? So that's the reason why operating systems are important. But do people care about the operating system? Technically speaking, no. Right? Whenever we use a computer system, we care about the word processor, the browser, we care about the specs of the laptop, the hardware, but nobody really cares about the OS. Right? The OS is simply the glue that puts the two together. But really, does it matter what your OS is? No. As long as your word processor works, or your game works, or your browser works. And most applications nowadays are accessible over the browser. So as long as your browser works, most users are fine. Right? So that's why the study of operating systems is important, even though it is a piece of software that people generally do not care about, particularly users that are not on the IT space. Okay. So what is an operating system? So let's get started with the class itself, right? So what is an operating system? Basically, it is the layer of abstraction simply between hardware and software, between your memory, your CPU, your network, and your disk, and between the applications that need them. That everything in the middle is actually called the operating system. So it is basically functions as a resource coordinator, who gets what amount of memory, who gets the CPU. It also allows virtualization technology. If you want to abstract applications to not see each other, you can create a virtual machine, which we're going to be using in this class. And it is also a reactive system. If something happens, it is the one responsible for appropriate reaction. For example, if an application crashes, can you see doesn't have enough disk space or memory? That is also the job of the operating system. So it's a very simple piece of software. And the reason why you want to have an operating system is you don't want application developers, like the maker of a web browser, email, or music player, or you yourselves, if you go into programming, you don't want to write directly to a piece of hardware. Why? Because as you see in the first slide, hardware moves very quickly. What is state of the art today, next year, 6 months from now, will not be state of the art anymore. That is the reason why it is important that applications write against what we call an abstraction layer, right? And that abstraction layer is basically a user interface program, that can be shared that runs on top of an operating system. And it's the operating system that keeps it consistent. So even if you upgrade your hardware, your software will continue to work. And even if the software gets upgraded, your hardware will continue to work. Do we have some questions so far, right, on operating systems? I think most of you should have. If you took IT related degrees, you should have gone through this already, right? For those who didn't, feel free to ask questions, but this is really essentially what an OS does, right? So one of the things also that operating systems are designed to do is that when an operating system exposes an interface to an application, the interface is what we call beautiful. It's a clean interface, it's easy to read, well documented, because applications, there are so many of them. There are way more applications than hardware types or hardware devices. And that's the reason why you have to create nicer interfaces so that application developers will not have a hard time because there are way more of them. Hardware, on the other hand, doesn't have a very nice interface because there are constraints of hardware that the operating system has to adjust to. And that's the reason why they have this saying, or at least this slide is showing, that the interface facing the hardware is ugly, while the interface facing applications are beautiful. All right. So this is now, in summary, let's take all of that together. An operating system essentially is a collection of programs that integrate the hardware resources of a computer and make those resources turn around, right? Make those resources available to the user in a productive, timely, and efficient manner. And these resources are used by the user through applications, right? So these are the things that operating systems ease the pain with. One is because the hardware interface is ugly, if you're a programmer, you don't have to worry about it. Just write against the beautiful OS interface. Most operating systems, particularly modern ones, Windows, Linux, etc., provide a high-level graphical interface, right? And this allows you to create applications without worrying about drawing on the screen a radio button, a box, a button, a form, right? You don't have to worry about those elements because the high-level graphical user interface is provided by the operating system, in which you just have to use them, right? Then multi-user and multitasking also is provided. Nowadays, computer hardware is quite fast, and most of us run multiple applications at the same time. Like me, myself, in this particular laptop, I'm running Zoom, I'm running a browser, right? So I'm running many pieces of software together, and that's what an operating system does. It manages all of these multitasking and multi-user applications. If somebody logs into my laptop from the outside, it can be done, right? That's why it's multi-user as well. And it makes visible the virtual component of the system, right? So if you want to create partitions like virtual machines, this is something that operating systems provide as well. And allows program interaction, right? Programs can use the resources, and at the same time, the other side, users can use programs. So why are operating systems difficult to create and maintain? Why are there only so few of them? Well, I think the major reasons people don't, quote unquote, buy operating systems per se because they like the operating system, but they normally buy the applications that come with the operating system. You may hear people say, oh, I prefer a Linux machine over a Windows or Windows over a Mac, right? That's a personal preference. But in reality, if you dig a little deeper, it's actually a question of applications they want to run. Oh, I want to run Windows. I want to run, Empire Games, etc. It has to be Windows. Or I want, for example, GarageBand. It has to be Mac. Right? So people tend to choose systems based on applications as opposed to based on the operating system themselves. Although a handful of people do prefer operating system or choices thereof, but that's rare and far in between. An operating system is also big. Right? Millions of lines of code. Linux, for example, is maintained by thousands of people around the world. It's an open source project. So it's very difficult to build and maintain an operating system. And imagine that together with the first point that there's really no additional value of the operating system itself, right? Outside of providing resources to an application, why would you pay a lot of money to maintain it. And that's the reason why operating systems, there are a lot of open source operating systems that are quite professionally done and well maintained, such as Linux, Unix, for example. These are examples of those operating systems. And of course, you want the operating system to be maintained longer. You don't have to worry about it being maintained. If you write your own operating system, you have to maintain it yourself, which will take resources and time. And if you don't want to maintain it anymore, then it gets orphaned. And that's the reason why operating systems require resources to continually maintain them as well. And of course, code that's written and rewritten many, many times, the original intent might have been forgotten, right? You may have written a particular application or particular routine for a particular function, but as you move along, you may have forgotten that original function. So these things just make operating system writing quite difficult. That's the reason why people tend to avoid them unless you are really in the operating system business, like Microsoft previously. Okay. Operating systems are also complex, right? They need to do different things, right? As I said, virtualization, input-output devices, resource management, handles errors. You have to consider all of these scenarios. Not only that, you have to deal with all the different types of hardwares you have to put into an operating system. So if you tried to run an old version of Windows, say Windows 95 today, it may not even recognize the memory of your machine, may not recognize your USB devices. That's the problem with outdated operating systems. They don't get updated as well with the latest and greatest hardware. That's the reason why there's challenges there as well, right? And I mentioned multitasking the last time. This is what a modern operating system looks like. It's not your application, beautiful interface, OS, ugly interface, and hardware. It's actually a lot more complicated than that. But in essence, there are two major portions of any operating system today, right? That lives between applications on top and hardware at the bottom. The two modes are called user mode and kernel mode, right? So let's start off with kernel mode. If you notice, kernel mode is the portion of the operating system that we know about and that fits the classic definition of an operating system. It essentially manages and provides access to resources, right? So if you notice here, it's responsible for process scheduling, for the IPC or inter-process communications when you send data from one process to another. It's also responsible for memory management, what memory is assigned to what. The virtual file system, especially when you store files, and the network file system to communicate outside of your system. All of these form what we call the kernel mode portion of an operating system. If we take, for example, a modern Linux operating system like Ubuntu, for example, the Linux kernel is the one responsible for running kernel mode of operations. That's an example of that. Now, at the bottom, you will have device drivers, the ALSA drivers for video cards, for example, the LVM drivers for your file system, device mapper for mapping hardware blocks to your file system, and so on and so forth. So these are the things that face your hardware. On the top, you will see user mode, right? So the user mode will have common things. The first part, the bottom is the C standard library in the case of a standardized Linux operating system like Ubuntu. You will see functions that are provided to access hardware. So instead of saying, I want to open a Fujitsu hard drive of 400 terabytes and go to 391 terabytes, you basically just use the open function, for example, to access a virtual file system which has the storage mounted and available to him. All right, so that's on the C standard library. Basically allows applications to write against it so that you don't have to write against the hardware. Now, modern operating system, in the olden days, C library and Linux kernel were enough. In modern days, there's a lot more things that go into your operating system. So we have something called low-level components that actually run on the user space. They're not in the kernel itself, but they are part and parcel of what we call the operating system. Right? System daemons are one of the most important. In Linux, you will have the system D, which basically manages which applications start on boot up, and how to manage, run, restart, reload configuration these applications. You will also have daemons such as Pulse Audio, for example, that manages the Linux sound system. So these are things, the reason why they're called daemons is because they're running on the background. They continually run on the background to provide their function. The second box here is what we call a windowing system that provides a graphical user interface to applications so that each application doesn't have to draw its own graphical user interface. That is the responsibility of the windowing system. This is also the reason why Windows 95 became a very popular operating system, because it had a very usable windowing system, which people like, and it was part of the operating system instead of being part of individual applications. That means every application in the Windows system does have a consistent look and feel because it uses a consistent windowing system. In a Linux distribution, that would either be X11 or Wayland are the two most popular ones. And Surface Finger is a windowing system for Android, which is actually Linux-based. Then you will have many other libraries, drawing widgets, providing browser interface, playing media files, and that would be that link there. And last but not the least is, of course, components that involve graphics manipulation. So Mesa being the most popular abstract or open framework for manipulating graphics, that is also available as well. So this is what your modern operating system looks like, and everything on top. The LibreOffice, which is the open source version. It's like an open source office productivity suite. GIMP is like an open source a picture editing application. All of this will access functionality provided by your user mode portion of the operating system, whether they're managed by daemons, are loaded in a windowing system, or use these libraries or the C standard libraries to do the function that they set out to do. Okay, questions so far? Don't be shy. All right. So again, this is just another view. This is a zoom in view. Again, it's still Linux, right? This is another way of looking at it. So we can look at operating systems in also a different way. Let's look at the hardware in which they ran on. So in the early days, you had what we call early systems or single-purpose computing platforms. They didn't need an operating system because the programmer basically accessed the application that was loaded directly in this hardware. There are a lot of these types of machines, and they don't even have to be electronic. For example, a typewriter can be argued to be a document processor that doesn't have an operating system, because the only thing it does is to create a document, right? So that's an example of this general purpose, single purpose. Then first real operating systems came out because they wanted to create what is called time-sharing computers. And because time-sharing computers were created, then you can batch the jobs. The reason why this was important is because you had computer systems that were scarce resources, and you have multiple users who wanted to use them. But you had to give them all computer time. And one of the ways to do this is to basically schedule jobs in batch. Right? And that's why batch processing was created. So who's responsible for managing, let's run application 1, then let's run application 2? That was the operating system. Right? So that's the original way in which operating systems were handled. In the past, it would be done by a person called an operator, who would actually bundle the jobs and run them when it was turned. Operating system was basically an automated version of your operator. Right? Then, of course, there's offline processing, right? In the case of online processing, when you do something, it's run immediately on the CPU, and the output comes out right away. For offline processing, it's sometimes done in banks, or in, like, for example, in credit cards, can do offline processing, where part of the transaction is done by one subsystem. It's taken offline because the other subsystem isn't ready. And when it's ready, it begins to power up again. In this drawing here at the bottom, this is one of those cases where the card reader reads the data from the system on the left, but the data doesn't move to the system on the right with the printer until an actual person takes in the data, the tape, from the left system to the middle system, where the person takes the tape from the middle system to the right system, right? So that's an example of offline. There's an offline portion in the transaction. Spooling is another concept for operating system where it's an extension of the batch process. And in this case, it's quite commonly used as a term for example, print jobs, right? So it's you batch the print jobs, they're put in something called a spool, which is stored in your disk, right? Simultaneous peripheral operation online spool. So you get the perception that the job is actually being executed, but it's actually waiting at the spool. Then when it's your turn to print, the printer goes through the spool, takes the first job, prints it. When it's done, takes the second job and prints it. That is spooling. Then, of course, because of all of those, there's limited number of users. People had to take their time, their turns, or people had to wait. Then there was the creation of something called multi-program systems, right? General purpose computers, like so pictured here, where they can do many jobs simultaneously in memory. They provide increased utilization. They were much more powerful than the earlier batch systems, and therefore they could allow multiple users to use them at the same time. This created the concept of time sharing or multitasking systems, where you will have many users using the same system. Now, the thing here is that computers were still quite expensive and rare, and that is the reason why they have to be shared. Then, of course, came the advent of what we call desktop systems. First appeared in the 70s, became popular in the 80s with the introduction of the IBM PC and the Apple II. Personal computers, as the name implies, is a computer bought by an individual. Therefore, the only tasks that that computer does are tasks assigned by you. Right? So instead of getting big, dedicated, super expensive hardware and letting people take their turns, the advent of the desktop system or personal computers allowed people to have computers of their own and run their own jobs in their own time, right? Which is what we have today. All our systems today are personal, right? Then, of course, as you needed more power, right, the desktop computer had to have more computing capacity, and that's why there was the advent of what we call multiprocessor systems. Because making a system or a chip faster has its limits in physics, because you can only make the transistors small, to a certain degree. Therefore, in order to increase performance, you add more CPUs or cores, right? And that's why you have symmetric multiprocessing systems or SMP systems. They're all CPUs do the same thing and they're of the same type. Now, symmetric multiprocessing is also possible. If you take a big data class, you're actually dealing with asymmetric multiprocessing, where the CPUs may not actually be the same, or each node in the compute cluster may also not be the same. And that's why it's asymmetric as opposed to symmetric. All the CPUs are the same, they do the same task. Right? There's also the concept of distributed or loosely coupled systems. In asynchronous, in the previous asymmetric multiprocessing, it is used in distributed systems where you can have multiple computer systems put together to perform a task, like a supercomputing cluster. Now, this one allows you to use the network as the interface between the two systems so that you have more processor and memory without necessarily increasing the processor at once, right? This actually allows you to build larger and larger systems without having to wait for improvements in processor or memory technology. But in this case, there's still some sharing that's done, so you can execute larger and larger jobs as well. The reason why this is called loosely coupled is because the integration between two machines are actually quite abstract. In this case, it goes all the way up to the network layer, as opposed to SMP machines, which are integrated at the memory layer. Okay. Now, this is a concept that we may not have time to demonstrate, so we'll just lecture it here. When you have a multiprocessing or a multi-core system, you have, for example, this one is an example of a 2-socket system with 4 cores per socket. So each socket here is, in this case, it's labeled NUMA node 0 and NUMA node 1. And inside NUMA node 0, you will have the processor. The processor's memory interface connects to the memory that's assigned to that processor. In this case, you have 32 gigs of memory per processor. Each processor in turn will have 4 CPUs and therefore 4 cores. Same thing with the other one. Now, any transaction that's done inside this is symmetric because all of these CPUs are sharing the same bus, therefore they're sharing the same memory bank. But what if CPU 0 wanted to ask memory storage from this memory in the other side? It's considered a remote access, which actually makes it slower. And that's the reason why when you buy computers, for example, I have an 8-core machine and I have like a terabyte of RAM. Why don't I give all 1 terabyte of RAM into one CPU or one virtual CPU? The answer is you can't do that because their memory in reality is broken down by NUMA boundary. In this case, I have two NUMA nodes because I have two processors. So instead of having one big 64 gig of memory, I actually have two 32 gigs of memory. This is very, very important because when you provision a VM and you're wondering, how come hindi na ma-maximize yung 64 gig of memory ko sa isang VM? It's because your NUMA bound is basically 32. That means any VM larger than 30 or 32 will have to cross, right, in order to do memory access, which is a lot more expensive. And that's the reason why for optimization purposes, pay attention to your boundaries. And last is basically clustered systems. So this one, again, you will discuss if you take a big data processing class, which I also teach actually. You basically take several CPUs or discrete computers together and you combine them to perform a particular task. This is also sometimes called parallel computing systems, right? In addition to being called clustered or clustering systems. They're most likely to share storage as well and networking because they have to have a common interface for you to access its content. Okay? Right. So this one is a specialty system, right? That you and I won't use under normal basis, but we are affected by it. These are what we call real-time systems. So they require a special operating system that basically allows execution in real time. Why do you need a real-time operating system in a factory? What happens when you try to run a program in your laptop and it's busy? You have to wait, right? But what happens if the factory that, for example, paints cars, a particular sensor is delayed because the CPU is busy? What happens to the car? If it was supposed to spray at a particular point, the late shot, the car wouldn't pass through and it's going to, the spray is going to miss its target. And that's the reason why real-time operating systems have are different from their non-real-time counterparts simply because of this case. Especially when you deal with, for example, healthcare, things that affect life and limb, like airline systems or here flight control systems, power plants. You need the systems in real time. You can't wait for an emergency scram, for example, the nuclear power plant, if your CPU is busy. That's why real-time systems are different from non-real-time systems. So for example, Linux is a non-real-time operating system, but it's a version of Linux that's real-time that's called RT Linux, which is uncreatively real-time Linux. Okay? So general structure of an operating system, you have two types of programs, resident and non-resident. Resident programs are loaded in memory and are always part of the operating system, right? Your systemd, your daemons are examples of resident program. While non-resident program like word processor, browser, Zoom are only loaded when you actually need them, okay? Right, and this one we already discussed. So again, the kernel mode is for resource management. User mode is you execute tasks on behalf of the users. That's why it exposes these libraries to applications so that they can execute in user mode. Right. And the last part, right, is process management. So this is already a quick overview of the entire SEM, right? So process management, I believe, is the last part of the semester where you discuss processes, memory synchronization, concepts such as deadlock or shared memory will be covered here. That will be covered by the other professor. Okay, but it is an important job of the operating system as well. Another important job is main memory management, right? The thing about operating systems is sometimes you don't have enough memory. And that's the reason why there's a concept called virtual memory, where it takes part of your disk and exposes it at memory. Of course, disks are slower than memory modules, but at least it's better than crashing the application because you don't have memory. That is part of virtual memory management, right? Which is also part of the overall main memory management scheme. So not only do you have to make sure that memory is allocated to the proper application, and of course, applications don't should not be able to see the memory of other applications for security reasons. That's the job of memory management. File management, on the other hand, handles your disks, right? These are more so for persistent data instead of for transient data, which lives in memory. Persistent data stays on the file system. File systems are created so that you can organize your disks that are exposed to your operating systems and thus your applications in a more simple fashion. Without an operating system, you have to write to each disk directly. If you have 100 disks, for example, it is you who have to determine which disk to write it on. Right? The file systems and file management allows the OS to do that for you. Right? And of course, it also provides some utilities to sort, index, and to track information in file systems. Now, file system is also input-output. When you write to a disk, that's actually considered an input. But there is also an input-output subsystem that handles other devices. So other device drivers, for example, your mouse, your keyboard, these are other input-output devices, actually low-speed input-output devices that can be integrated into your system. Then you have secondary storage management or free space management, which is also an important job, right? Outside of primary storage, secondary, and of course, networking to be able to compute different nodes or computers together. We wouldn't have the internet, for example, or we wouldn't be able to have this class if we didn't have our networks working. Okay. Right. These are some other subsystems. Protection subsystem basically allows an operating system to partition memory. Right. This memory is only accessible by this process. Enforcement of the protection makes a system more secure. Again, original systems may not have focused on security too much, but in this day and age, it's very important. And that's why this function protection system is important as well. And the very basic, super basic way to interact with the operating system is via command line. And that's the reason why you have a command interpreter system that takes in the commands and runs them on behalf of the user. However, in these modern times, most interfaces are graphical. You have buttons to click, etc., which makes computing a lot more accessible to people. That's the reason why this system is important as well, because this is what interfaces with you. Operating systems can also have different architectures. Monolithic kernel, because this usually refers to the kernel portion of an operating system. Monolithic kernel means all functionalities inside the kernel, memory management, process management, and the like, are in one process that runs in memory. As opposed to, for example, a microkernel architectures, you still have a main kernel, but you can farm out a smaller kernel processes certain things, right? So to take a look at an example, let's see, let me share. So I have a running system here. We can take a look at. So for example, NUMA. So NUMA stat will tell me the NUMA hits, meaning I tried to access a piece of memory that's within the NUMA boundary, and the NUMA miss means it's that NUMA boundary. I had to cross to the other side to get it. So this means my laptop was, I didn't really use the other, I didn't have to cross, right? And the reason for that is because my laptop only has one core, right? This is a laptop, so it's an i5. It has one core. You can find out that in Linux. We will actually learn more about this later, but there's a file called CPU info where you can see information about your CPU. So I have how many cores? 1, 2, 3, 4, right? So processor 0 until 4. But this is basically cores in a single socket. And that's the reason why my NUMA stat will not show any movement, because I only have one socket. But if you run this on a server, you will actually see a difference there. So I have a 4-core Intel i5 720U, for example. That's my laptop, right? Now, what's that I want to show you? Microkernel. So PS is a command to show the process that are running. So PSEF is like show all processes in detail. So let's look at the top. the first process is always a, I've been running this for a long time. So you will see different kinds of process here, but process zero, process one, process zero is actually the kernel, right? So process one, whose parent ID is process zero, this is the kernel, is the first process in any Linux system that runs. This is actually systemd. It's the first user space application that runs, and it's responsible for running all other user space applications. And you will see all of this in parentheses. These are actually kernel processes, because modern Linux operating systems are no longer monolithic, but they are microkernels in architecture. That's why you will see different processes here handling different things. For example, the IRQ, or the interrupt request daemon, is actually run as a separate kernel process in a microkernel architecture. So there's quite a number of kernel processes here, right? And regular processes are these, right? Not hidden in parentheses. Audit.d, for example, it's one of those applications that they keep track of utilization in your system for audit purposes, for example. dbus broker is a bus system that allows components in a graphical user interface like GNOME to talk to each other. These are all running in user space. The ones in parentheses are running in kernel space, right? So that's just a quick view of an operating system. What's in it? All right. So that's Linux in that case. Okay, let's go back here. So just more details. You will see that monolithic architecture. Okay, that's not blinking lights. Right, means the entire kernel functionality is just in one operating, is in one process. So everything is one process, one big kernel, and all user programs call it. It's not very common anymore. You'll have a layered operating system where operator talks to application hardware here, and it's passed through layers, right? Again, not so easy to implement because a lot of these functionalities are actually used at the same time, like main memory management, process management have to be used at the same time. Virtual machine is a concept where VM provides a copy of the hardware. So the process thinks, operating system thinks that they're running on different hardware, but they're actually running on a virtual machine, its own kernel, and the process running on top. So it's an abstraction layer. It eats up resources, but at least it allows you to, run applications that don't behave well if they have to run together with other applications, which is quite common in servers. Or in this class, right? If you have a Windows or a Mac machine, and you want to run, say, Linux, you can't run Linux, for example, and Mac OS X at the same time. So you have to put a virtual machine so that you can run Linux. Okay. Containers are a more recent level of abstraction. In this case, instead of a virtual machine where you have one host operating system, the hypervisor, which provides a virtualization, and many operating systems on many VMs and their own libraries and apps. In a container model, you notice there's no hypervisor, which is replaced by a container engine. But notice that all the apps share the operating system of the host. Right? In this case, this operating system shared. So there's no separate OS each. It is a layer of abstraction that's less abstracted than a virtual machine, but clearly it uses lesser resources than a virtual machine. And last, of course, is the microkernel architecture. Again, more modern operating systems like this, and I showed you with the PS example on Linux a while ago, where each of these little processes, I saw thread manager, also file system manager, are actually system processes that run separately from the main kernel itself. That's why it's called microkernel architecture. Okay, questions so far? Yeah. Right. So now for this class, we're going to cover Linux, right? So that is the main topic for the class. Oops. Let's look for slide number 2. Slide number 2, promise, is very short. Oops. Damn it. All right. So slide number 2 is just a quick introduction of Linux because we're going to do a little hands-on later on. I'll just have to show quickly evolution of Linux. Again, we don't have to boil the ocean here. Okay. So here, this is basically an introduction to the Unix operating system. The previous slide goes through the entire course in a short version very quickly. That's actually your entire course. That thing I just said a while ago in less than 40 minutes is everything that an operating system has. Then the rest of the semester will basically be covering details of each of those things, right? So what better way to learn about operating system than to use an open one, a fairly, structurally understandable operating system such as Unix, right? So today we'll cover, for this course, at least my part of the course, we'll cover the evolution of Unix, Unix structure and system calls, and shell programming. Will be some of the things we'll be covering in the first half of the class. Okay. So first off, Unix was invented by two developers. So first Ken Thompson and then Ennis Ritchie invented the C programming language. They were basically developing in a machine called the DEC PDP-7, which was not being used at the time in their lab, which is Bell Lab Laboratories, which was part of AT&T, right? So they were working on many things, right? And one thing that they worked on was basically they used the C programming language, which they invented, and developed Unix on top of C. And what was the reason for doing so? Every time they had new hardware, like in this case, a PDP-11, they'd have to write their applications again. So every time they move from PDP-7, I write my application. But when the new box arrives, I rewrite my application to run on that. That's why all application came in source code, and you had to recompile them. And you have to rewrite them because the instruction set may not be exactly the same. Then we'll move it to even newer systems. That's the reason why they decided, hey, let's write it in C, right? Let's write Unix or the little layer operating system in C so that I don't have to keep on rewriting it. I just have to recompile it every time I move from system to system. This made it a lot simpler. And when I write an application on top of one operating system, it's only the operating system that I have to adjust, right, to fit the new hardware. So that was the logic then. And they added more examples, multiple programming, threading, etc. were added on as years progressed and became popular, right? So they distribute version 6 outside the Bell Labs, and there are quite a number of licensees. Majority of the Unix operating systems outside that call themselves Unix, such as Solaris, AIX, HPUX, are actually descendants of this original Unix because they were licensees. Now, of course, Unix as a standalone operating system is getting less and less popular. I still see some Solaris and AIX usage, but majority have moved to Linux, which is not Unix per se, but really. Okay, so version 7 came out and was developed for the PDP-1170, so the newer machine, right? And this is the base for majority of Unix systems out there, right? So that's why you see sometimes they call Unix, you're a system V Unix, a system 5 Unix, which is related to the Unix that is here. Right. One of the benefits of Unix is it was standardized from day one. Its design was clean, right? It was basically meant to be an operating system from the start, and many academic institutions and organizations contributed to Unix. Right. So here's the first Vax work, as presented a while ago, right? And Bill Joy, for example, worked on to produce 3BSD, which is a Berkeley standard distribution, which was a version of Unix that was developed in the University of Berkeley, University of California in Berkeley, right? Implemented such functionality. Now, I'm not sure if you're familiar, but Bill Joy is a popular name. He's also the founder of Sun Microsystems. So clearly what he learned while working in Berkeley, he took and he used to found Sun Microsystems that developed subsequently its own flavor of Unix called Solaris. Then, of course, many organizations contributed, not just schools, but even DARPA funded quite a lot of work on Unix. And it was developed as a standardized system for government use. The project led to 4BSD, newer version of 3BSD, which was basically distributed with source code by the University of California, Berkeley. And it was also the version of Unix that came with the TCP/IP stack. For those of you who do not know, the TCP/IP protocol is the protocol that drives the internet that we are using today. Again, no Zoom without internet, no internet without TCP/IP. Therefore, it is important to know that this version of Unix is one of the most widely distributed versions of Unix simply because it had the internet to distribute it with in the early days. And that's why this version of Unix, particularly BSD Unix, became very popular as well. Right? Then you will notice there will be newer versions of BSD Linux, Unix, or now 4.2, introduce other functionalities, local area network. At this time, our ARPANET was only 60 nodes, 1984. And as soon as, right, not even 10 years, it has reached 8,000 nodes with 10 million users. Now we could easily say there are like 6 billion internet users now. So it's large. Right? 4.4 is the last BSD release. So you will notice also that the versions of TCP/IP align with the versions of BSD. First version of TCP/IP is 4.0 BSD. There's a 4.1, 4.2 BSD, and there's a 4.4 BSD. So the fortunes of TCP/IP followed the fortunes of BSD, but even as BSD became less and less popular, TCP/IP as an internet protocol still retained its popularity. Right? It spread outside of the university systems and Bell Labs, and many people started to develop their own flavors of Unix. So again, Bill Joy moved on to set up Sun Microsystems using BSD to run on workstations like a personal Unix machine. The DEC folks created Ultrix and OSF1, right? They are the inventors of the Alpha processor, which is a competing processor to Intel, although Intel won that war. Even Microsoft had a Unix distribution called Synix, and Santa Cruz Operations had a Unix version as well called SCO Unix, right? And of course, Santa Cruz Operations later on started to carry Unix as well. Again, many standardizations, a lot of the Unix operating system is actually quite standardized and it follows general industry standards. That's the reason why it's also possible to get inter-Unix interoperability. One of the most common standards is what we call POSIX, right, which is basically a standard interface that Unix systems expose and even Linux systems expose. Right, and as we wrap up this session, you will see various descendants of operating systems. You'll see from the top, the original PDP-7 operating system gave birth to Unix version 1 to 4, and you will see the spin-offs. Notice the ones with plenty spin-offs. The System 5 Release 4 has a lot of spin-offs, and BSD. Right? The entire BSD 3 has a lot of spin-offs. You will notice Linux here is just a Unix-like operating. Technically speaking, it is not Unix. It's just Unix-like. So you'll see Minix, which came out first, and the Tandem Moms operating system for learning. And Linus Torvalds released Linux, and this is the Linux tree. So Linux, again, is still the most popular Unix-like operating system, but there are still many other Unix operating systems. Another Unix, actually this is a real Unix operating system, is Mac OS X, which is descendant from BSD, right? So it branched off from BSD, went to a company called Next, which is where Steve Jobs worked. He founded it even after he left Apple the first time. He rejoined Apple. He took the core of Next Step and made the core of Mac OS X. And it is also the core of OS X that's in your mobile phones today. Right? So that one came from Next Step, and it's the core of what we now know as Mac OS X. And these are some other flavors. These are the open source ones, like FreeBSD, NetBSD, and OpenBSD are also quite popular. Not as popular as Linux, but they are popular as well. And you will have the commercial Unixes. The one that's still probably around is AIX and Solaris. Okay. Before we proceed, please download. Okay, that's not the latest version, right? So that's not the latest version of the ISO, but there will be an ISO version. Then download a application called VirtualBox, right? And don't forget to install the EPEL packages. So now I will go through that. But before I proceed, are there any questions on the history of Unix and Linux and operating systems in general? Wala. Okay. So let us now start to do this. I mean, if you already know how to install Linux, that's great. Just watch. For those of you who don't, it's okay. Now, I'm using a Linux operating system. So for me, it has a command line and all of that. So it looks like a Linux operating system. So you'll notice, right, I have a command line right here. But I'm going to install Linux in my Linux operating system. So first off, I downloaded where's my operating system? Oh, I don't have an installer. Okay, so I have to download one pala. So let's go here. So first things first, let's go to CentOS. Okay, the problem with CentOS is it's end of life na, but for us, it's good enough for our class because we don't really need the latest and greatest of any particular operating system because we're not using specific software that need to load. So we can use older version of CentOS. So this is the current maintained version of CentOS 7. Let's go to the x86 version. All right. And I will download. So let me install the minimal. All right, so this one. So you download it to your system. Now this is a gig, so it will probably take a while, right? So let's let that download first. And I'll show you what VirtualBox looks like. So there are many virtualization technologies, but for this class, we use VirtualBox for the simple reason that if I show you how to use it in Linux, it's also how you use it in Windows and how you use it in Mac OS X. Now, if you, for example, sir, I'm more comfortable with Parallels or VMware, feel free to use whatever virtualization technology you like. Right? So there's no requirement in this class to use a particular virtualization technology. But this one, I'm just using this because it is cross-platform. So instructions I show you in Linux, because I use Linux as my main operating system, will also apply if you are in Windows. Let me just do some housekeeping, since that was my previous class, which I don't need anymore. And I will show you the VirtualBox website while we're waiting for the ISO to download. So VirtualBox is an open source project. It's now owned by Oracle. So you can download VirtualBox here. You will notice if you go to the downloads page, there will be different Virt packages, right, that can support. You have Windows, you have Unix. So there will be many ways to install Windows, OS X for Mac, and Linux, various Linux distributions. Now, I installed VirtualBox that came together with my Fedora operating system. If you're using Ubuntu, you can also install VirtualBox directly from there. If you're using Windows, you have to download here. And since most of you use Windows, you can actually use this link over here. Okay. So, I clicked on it twice, therefore it downloaded twice. So this is the Windows. So if I open, I'll see, oops, the open show in folder. So my download folder now is the VirtualBox installer. Of course, it will not install because I'm using Linux, so scrap that. And now I installed my CentOS ISO OS so that I can start to install my operating system. Oh, by the way, there's also a syllabus in case you haven't seen it. Again, it's a synchronous class. Syllabus is here. All right. So let's install. So first off, load VirtualBox and select new. Name your operating system, IT250. Let's call it IT250. It's okay. That's not Fedora, but you can call it other Linux system because there's no CentOS. Well, it's a Red Hat technically speaking. Okay, so Red Hat 64-bit. Give it the amount of memory you need. In our case, 1 gig is more than enough. Again, please take note of how much memory your laptop has because it's installing it there. So let's not give it too much. I will create a new virtual disk because it's a fresh install. We have this joke in Linux. If you don't understand what you're doing, just say yes to the default. It's probably correct. Like this case, I don't understand the question. Thanks. All right. So this one is just the type of images. This is a VMware compatible VMDK, and this is Hyper-V compatible VHD. Okay. Dynamically allocated means that even if I say 8 gig is my disk, it won't automatically provision the 8 gig. It will actually only write to the disk whenever I write files into my VM. Now, the danger there is that if you run out of space before you're able to use the 8 gig in your virtual machine, you will also run out of space in the virtual machine, even though the virtual machine thinks you still have space. So just be careful about dynamic allocation because it only allocates the memory from your host when you need it. Okay, 8 gig is fine because it's dynamic end anyway. Now, before I install, I need to do a few things. Right? Number one, I need to mount my installer. If I were installing in a physical system, I would either plug in a USB drive or put in a DVD. Since I download the ISO, I'm going to have virtual DVD here. Right. Optical disc selector. There, it actually saw it. It's great. So now this one will boot the machine. Right. Now this one I don't need anymore. Let's start with that. So this is going to boot. So then when I start this virtual machine, it's going to boot the contents of that installer, right? The second thing I have to set is my network. Now, there are some challenges getting internet connectivity on VirtualBox. And that's the reason why I normally tell students, enable NAT so that your virtual machine can access the internet. But if you want your host to access your guest, enable another network called a host-only adapter. And wait, there is a problem here because I have no host-only adapter. So let's exit this first. Go here to File. So if you have no host-only adapter, you have to create one. So I create a new one here. What's the issue? Oh, okay. This is a problem only in Linux, right? So you don't have to worry about this if you're using another operating system. But the problem with Linux is, especially Fedora, is every time I upgrade my kernel, I need to create new drivers, and sometimes it's not installed properly. That's why I have to do this, because I have to do device signing. So it's going to upgrade my VirtualBox, right? It's going to upgrade the kernel as well, and it's going to sign it, which is done, right? But you guys don't have to do this. So you can go back if you're not using Fedora, by the way. So here, this should work now. So there's VBoxNet 0. The default is fine. Then you go back to your virtual machine. Right, details. Settings. Right, then go back to network. Network adapter. Adapter 2. Create something called host-only adapter. Then you can also VBoxNet. And make sure it's checked enable. Then you're ready to install. And click start. And it will now power up a virtual machine. The virtual machine says, am I going to pick this optical disk? Yeah. So it's going to boot off that disk because it realized the hard disk has nothing inside. So I boot off that disk. Let's make this a little bigger. So anyway, just install directly. There's no need to test media because we downloaded it from the internet and we assume it's fine. So, right, let's wait for the GUI to boot. So this is actually booting Linux right now. Again, this is all recorded, so I'll upload it when it's done. So you wait till the installer boots. Okay. So this is what we call a minimum installer by the way. It still has a graphical user interface, so it's still quite convenient to use. But it doesn't have all the software packages, so it won't give you a choice about software packages. And we're not going to need a GUI for this class, so I'm not going to install a GUI so that it doesn't take up too much space. Okay, here there's English Philippines, apparently. Continue. All right. So things that have the exclamation point are things that you're supposed to do. The rest are all optional, right? And if you notice, they what you call it? Blurred themselves, right? So in this case, date and time zone variation Manila, that's correct, right? Language support English Philippines, keyboard English, which is what we selected. The installation source is of course local media, because you're installing it from this ISO. So again, there's no need to change that. Software selection also has no choice because we only downloaded the minimum ISO. Kaya 1 gig lang siya kasi lang siya. Right? Then, installation destination, right? By default, automatic partitioning is selected, but it won't let you do it until you click on it, right? So even if you look at it, it says automatic partitioning is great. We can leave it as automatic and just say done. If you notice, it will disappear and says it's fine. This is for troubleshooting. You have to do this. Don't forget to do this. You have to enable the network. This is what students normally forget. Yung problem nila is they don't enable the network. Therefore, when this boots, does not work. Also, you give it a nice name. But when it logs in, it has a nice name, right? It's ITT 250, right? Let's just call it that. Apply. So if you notice, since I created two interfaces, I'm going to see two interfaces. One is what we call the NAT interface. This is what's going to be used to access the internet. The second one is called the host-only interface. You take a look at this number here, 192.168.56.11, basically allows you to connect to this virtual machine, right? Later on, after we install. Right. So the configuration is fine, right? Security policy, we don't need secure Linux, so let's keep that off. And begin install. While it's installing, you notice it's going through the installation here. You can do other things, like set the root password. So normally, we suggest you use a strong root password. Okay. Sweet. There you go. Strong. So I now have a root password. And I also create my own user. So normally I create one user because it's normally not best practice to use root when you're working around a system. So what you can do is you can create a user, your own user, and just give it administrator privilege. So check this box here, right? That means you can do administrative actions later when you need it only, right? So which is much safer. Yeah. Type of password. Right. And we are done. So I'm using a weak password because I don't want to forget for this class. It doesn't allow me to use a weak password anymore. Okay. Let's take a strong password. Passwords, not much. Let's see. Passwords, not much. There you go. Okay. Anyway, now since it's a minimum install, it doesn't take much. If you notice, it's just right. We're already halfway through. So there, that's actually how we install Linux operating system, right? Again, we'll just wait for that to complete. You will see here a video on an introduction to Linux by the Linux Foundation, and you'll see some instructions here. On this instruction here is actually what we're doing right now. Right, let me arrange these things so that they are in the proper sequence. Right, so this thing installing should be before SSH connection. All right. So let's look at this installing CentOS 7 VirtualBox. So notice we're installing exactly CentOS 7. All right. Although this is not the version that we're using, but you can always use the newer one. Wait, what are we using, by the way? What are we using? Minimal 2009. So let's edit it so that, because the nice thing about this is you can edit it. Where's the edit button? Okay, right. There you go. We can edit that. See? Sure. Let us. There you go. And this one is to install, create VirtualBox bridge mode. But we don't do bridge mode anymore, but we created a host-only adapter. So if you notice, we use that setting here. We configure this. See? So I'm editing my materials for you. There you go. And if you forget your password, and if you forget to boot a device, there's also some instructions here. Again, it's so common that you students forget this, that they actually write instructions on how to fix it, right? But again, if you forget your password, that's there. If you forget to start the network on boot, that's there as well, right? So again, these are the instructions, but the video exists also, so we don't have to worry about that. Then your lab exercise number 1, I will enable, right? But this is still due next week, right? So again, it's not due at the next class time, just to take note, it's due next week, right? So it's a week to work on it, right? So again, please take note of the dates. And let's go back to our installation. Right, we're done. And so post-installation tasks, we are nearly finished. I think we should end the class on time. Okay, so this is important because we can do things like partition and file system manipulation using this. If we do AWS, it doesn't generally allow you to be creative on how you partition your file system. So there are certain things we do on AWS and there are certain things we have to do using this. So make sure when you're done with this class, if you were following, that's great. But if you're not able to follow, make sure you go through the video and install it. That's your lab exercise number 1, simply to replicate what I did here. Okay, so the instructions are here. These are the 2 instructions on how to do these 2. All right. Again, they're due at the end of the week. Okay, not on our next class. Okay, this is taking a while. All right, so maybe if you need to run to the restroom, then now is the best time while we're waiting for this to complete. Okay, let's wait a bit. All right, but if there are questions, please let me know. And any questions so far? Quiet. Perfect comprehension, Dani. No any questions. Okay, that's generating the initial RAM file system, right? So instead of installing stuff when it boots an operating system, you load a file called the RAM FS. So that entire RAM FS is loaded into memory directly. This actually improves boot time. It's good as well. Now you're successfully booted. All right. Hope you guys are still there. Let's reboot. Okay, so now a little caveat. Since I'm using Linux, it's easier for me to log into a system because I have secure shell installed. Right. So just boot. So here, boot up process should be fairly fast because it's a minimal operating system. So even if boot from scratch is not too bad. You can log in. Right? And I'm logged into the system. Now notice it's not very readable, right? It's very small again. So you can put IPA, will tell you the IP addresses. You notice there are three interfaces, 1, 2, 3. Loopback interface, for those of you who took networking, is simply the IP address to talk to yourself. So if you look back 0, that means you're talking to yourself. So sending a message to 127, this is the IP address, 127.0.0.1 is sending a message to yourself. The second interface is what you call your NAT interface. We configured this, right? So if you remember a while ago, this is your NAT interface. This allows you to access the internet. So if, for example, I ping the internet, example, should work, right? Because again, I have access to the internet. All right, let's pick something that actually does work. Google, right? So that passes through interface number 2. Now, if I want to connect to this machine from my host machine, because this is a guest inside the VM, this is a machine within a machine. I want to connect to this machine, then I use number 3, right? And this is the IP address of number 3, which has no IP address. Let me see again. So, something missing. I look at my installation here. Basically, I'm supposed to go to configure my local network. So network scripts, that is if config enp8, right? Notice the on boot is no. So I make this yes, but VI is a text editor tool, allows you to edit. You can also use Nano, I think it's easier to use, but it's not installed by default. So VI is great to learn because it's installed by default. But before that, I put sudo in front of it, makes me a super user. By typing VI alone, I'm a regular user. You see the dollar sign there? That means you're a regular user. putting sudo on top gives you more power, and then I can edit this file now. Right. Then it's edited, and I can restart the network. So system CTL restart. All right, then I have to be super user. All right, and it resets the network. I look at the network again, and 10.168.56.11. Now I can go to my Linux machine and go to 192.168.6.11. For the first time, I have to say yes. When I log in, oops, strong password. Okay, I'm logged in, right? See? So again, if I'm logging in through my main system, and you notice it's easier. I can increase the font size and make it clearer. Just to go back to what I showed you a while ago, IPA, right, shows you the network interfaces. At least this is clearer than the one a while ago. First one's loopback interface. Second one's your NAT interface. Third is your what you call host-only interface. It allows my host machine, this Linux machine, to connect to that machine. Now, if you're using Windows, you can't do this. Therefore, you can do this. So AWS, no, it's not it. It's not. Use an application called PuTTY. Search for that. There, putty.org. You can download this in your Windows system, and you can type the IP address and the username, and you will get an interface that looks like this. This is called the command line interface. The simplest possible interface on a Unix system. Now, in this particular case, I just showed you how to know what IP addresses you have. You notice I connected to this IP address because it is called a loopback interface, right? So now I'm connected to the machine and I can do many things. Now, kanina hindi kasi nag-boot yung loopback interface na to. That's why I used a tool called VI to edit the configuration file. Now, the configuration file of the network is always in this folder in that ifconfig. So you see the two networks there, right? I edited one file. If you notice, without putting sudo, which sudo means super user do, right? I open it as a regular user. And if I try to edit, so I press I to go to edit mode in VI. It says warning, changing only read-only file. Once I'm finished, I press escape :Q to quit. So again, once I want to edit, I press I. I can try to edit it, but since, so for example, I make it snow and I try to save, escape :W, for example, save, it will fail. Even if I override it, it will fail because I am not a super user. So Q exclamation point means force quit. Now, in order to really edit it, I put sudo on front. Super user do VI to edit, right? And the super user, I type my password. Now I'm in. I can edit this. For example, I make this no, right? So I to go to insert mode, you see the word insert. This is not insert mode. If I type, it won't work, right? Because it's a command mode. I have to type I, right? Insert mode, then I can type the text. Say make this yes, back to yes. Once I'm done, press escape to go back to command mode. Press :W to save, Q to quit. That, right? And that works. To restart the network, I use the command called systemctl, right? By typing systemctl alone, it tells you what are the system daemons. So this is a way to interface with your process number one, which is systemd, right? So here, you can restart the network. Of course, I don't advise you restart the network at this point because I am remotely connected to this machine. Right? So I can hit the status na lang. There, it's right. Okay. Questions for the class? So that's it for today. I think it's a lot of material to carry in one go. It's quite fast. But I suggest your goal is really to make sure you get lab exercise number 1 as fast as possible. Try to connect remotely to it. Show this. You can actually do host, uname. That's there. Now, what I normally tell my students to do once they install a new system is to update first. Of course, you can install something called EPEL release. I think this is important because it includes certain applications that are easier to use. For example, VI as a text editor is not a very easy to use text editor, right? So most people aren't too comfortable using it. So I suggest they use VI. Nano, right? So Nano, you can install it. So this command, by the way, sudo, you notice again, super user do, yum is yet another upgrade manager. I think that's what yum means. And install is a command. So this one is install nano, right? Kanina I said install EPEL release, right? So now I can do nano, edit that configuration file a while ago. So the reason why I know is because I quite memorized it already after years of teaching. Right. So nano is easier. There's no escape, right? You type what you like a regular text editor. Make it yes. Then once you're done, just press Control X. It'll ask you to save, yes. And you're done. Then it said permission denied because we're not super user. So you ask to save no. And you put super user do, right? You can edit it. Let's edit it. Yes. Control X to save, yes. And this one actually works. Okay. So normally you can also do yum update. I suggest you do this just to ensure that you're using the latest version of stuff in case there's a vulnerability. But do it when your internet is fast because again, like the ISO file was 900 meg, right? It's nearly a gig. The updates are about a quarter of a gig, like 250. Last time I looked, right? But it's always good to do this because there are security vulnerabilities on it. Okay, that is it for today. May I hear any questions, comments, or violent reactions? Wala na?
Hi, Doc William.
Yes.
Double check ko lang po. Dun sa dialer po, wala pa po yung lab works?
Yes, it will appear later.
Okay. Tapos, Doc, isa pa po. Tinry ko pong i-open yung yung Academy Learner. Then, there's vocarium.com. Nangingi po siya ng user ID and password?
If you feel, diba, when you click on the email, you're going to get a user ID. You're going to be able to register your username.
Opo.
So from AWS Academy. So if you get the Vocarium and it asks you for username and password, actually the proper one is you can actually, ito lang yun you username ng AWS Academy is your email address AWS Academy, di ba?
Yes, sir.
And you have a password. The username and Vocarium is the same, except that you remove the .AWS Academy at the back, and it's the same password.
Okay. I will try it later.
Now, worst case scenario, if it's really does not work, in the Vocarium screen, you can actually click, I forgot password, and it will reset it.
Okay.
Okay, but try that first, just dropping. So if you log into AWS Academy, you have to put the .AWS Academy. But if you log into Vocarium, in the Vocarium screen, you just remove the .AWS Academy at the end and just use your email address.
Okay. Thank you, Doc.
All right. No problem. Who else? Questions? All right. Kung wala na, I'll see you guys tomorrow at 9. Okay, so let's do 9. Let's try to keep it 1 hour lang para, there's not enough. But what I'd like you to do is at least try a little, to do a little installation and the like, para if there are questions, we can discuss it tomorrow. All right, is that okay?
Yes, thank you, Doc.
Okay. All right, so thank you very much, guys, and have a good weekend. See you tomorrow. Bye.
Thank you, Doc.
Thank you, Doc. Goodbye, Doc.
Bye, Doc. Bye, classmates.
Thank you, Doc.
Goodbye, everyone.
Bye, everyone.